Good morning. We are working on momentum and problems that involve both momentum and energy. So quick recap. Let's just do a quick review of a couple of the things that we've learned and techniques that we use currently. Work and impulse. What is work? In the general case, work is the integral of f dot dx, right? It's the area under the curve when we plot force versus distance. The area under that curve is equal to the work done. And work is linked to change in kinetic energy. Impulse, we get a very similar thought process, very similar set of information. Impulse is the integral of f dt. When f is constant, it's just force times time. But if f is not constant, it's the integral of f dt. If we look at force versus time, it's the area under that curve. This is a vector quantity. Impulse is change in momentum. If our force is, we could also view it as the average force, right? F average. And we know that there's going to be a certain change in momentum. Lots of times the change in momentum is fixed. Like for example, when you were driving down the freeway, you had a certain momentum, your car crashes into a wall, you have zero momentum. Your change in momentum is fixed. But we can change the average force acting on you by spreading out the time interval that force acts. We know it's going to take some force to change your momentum from maximum value driving down the freeway to zero. It's going to take a force. If that force acts over a very small time interval, it has to be a huge force. Not good for you. If that force can act over a longer time period by barreling through, by crashing through some of those barrels filled with sand, and then the front of your car crumples, and then the airbag goes off, all of those things are designed to spread out the time interval where you're changing your momentum. And what does that mean? That means that a much lower average force is needed to achieve the same change in momentum. Another example is if you've ever shot a gun, a lot of times when you shoot a rifle, it has recoil. Rifle rests against your shoulder and there's recoil, right? Because when the bullet comes out with a certain amount of momentum, what does the gun have to do? It has to go backwards with the same amount of momentum as the bullet coming out the other end. The gun is much more massive than the bullet, so it doesn't come back with as much speed as the bullet comes out, obviously, but it still recoils and hits your shoulder. And they sell all kinds of devices for guns to, what they say, reduce the recoil. Can you reduce the recoil? No. If the bullet comes out with a certain amount of momentum, the gun has to go back with the same amount of momentum. What do they mean? They mean that how much recoil you feel. They spread out the time interval, right? They make the curve look like, from this is what it would look like, force versus time. It would look like this, right? A really big force for a short period of time. But what does it do? It takes that and it spreads it out. You buy something, maybe it's a some kind of spring shock stock for the gun, so that when the gun recoils, there's a spring in there, a shock absorber that takes in some of that. What is it doing? It's taking a curve that looks like this and converting it into one that looks like this. So the maximum force is much less, but they've spread out the area. The area under the curves has to be the same for both of these. One of them achieved the same change in momentum without exerting a very big force by spreading out the time interval. Okay. All right, let's do another example problem where we need to use both energy and momentum. Kind of focus on that. I think we'll see. Maybe we can start center of mass today, and we'll finish it up on Tuesday. Okay, we've got two blocks at rest. Have this be 5 meters, 30 degrees. Let's make this frictionless. Two kilograms and 3 kilograms. How's that? So what happens, we're going to release A. It's going to slide down the incline, slide across the horizontal surface, collide with B, and they'll stick together. We want to know the final velocity of those blocks. Okay, I'll give you a minute to think about it. No friction anywhere. No friction anywhere. So can we go, we're trying to figure out how to solve a problem, right? Let's think about what tools we have. One of the tools that we've used a lot is conservation of energy, right? Can we go from the beginning to the end using energy? No, because we know there's a collision in between, and we know for certain in this case that the mechanical energy will be different before and after the collision because they stick together. We know that's inelastic for sure. Can we go from the beginning to the end using momentum? No. At the beginning, there's no momentum. At the end, there is momentum. So something's not right there because the Earth acts on our system. The Earth pulls on block A and gets it moving. And we can't include the Earth in our system because it's basically an infinite mass, right? We learned that last time. So what do? We break it up into two problems or more. Sometimes we need more than two problems. I like to make a timeline. What two times do I always have on my timeline? The split second before the collision and the split second after the collision. So just before the collision and just after the collision. Just before the collision, A is coming along, moving at some velocity. I'm going to call this 2. And B is just sitting here at rest. And then after the collision, I'm going to call that time 3. They're stuck together and moving with some velocity v3. Just before the collision, just after the collision. Now I say, well, what happens afterwards or what happens before? It turns out that something happens before that I need to consider. So I need earlier. I need an earlier time on my, and I've got A sitting up here. Okay. So I'm going to go from 1 to 2 using energy to find the velocity of block A, the split second before the collision. Then I can get through that collision. I can go from 2 to 3 using momentum. Because I know I can always get through a collision with momentum. The energy at time 1 has to equal the energy at time 2 because I have no friction in my system, no external forces. Right, we're trying to find V2, the velocity of block A when it gets to the horizontal surface. So you see, as you get good with energy conservation problems, when you get a simple one like this, you just have one object going down a hill, you're trying to find its velocity. You probably don't need to make a bar chart for that. If you do, that's fine, make the bar chart. But I kind of reserve that when I have more complicated problems. And as you get more and more familiar with it, then you can, maybe you don't need the bar chart. But I think it's a great way to start out, especially with complicated problems, and especially when you're just starting out, because it really kind of helps train your mind in thinking about the problem correctly. So for my energy conservation problem, I've got E at time 1 equals E at time 2 because I have no friction in my system, no external forces. And that means that this is mechanical energy, of course. I'm starting out, all the mechanical energy is in the form of gravitational potential energy. And at the end, it's all in the form of kinetic energy. And this tells me that my velocity is the square root of 2gh. And what is h? H is this height h is equal to 5 times the sine of 30 degrees. Is that right? Yes. I have confirmation. Now we can go with momentum. The momentum at time 2 has to equal the momentum at time 3. Pick a direction as your positive direction. This is a vector equation. The momentum of A at time 2 plus the momentum of B at time 2 is the momentum of A plus B at 3. And we know, of course, B is not moving initially. It has no momentum. And they're stuck together at the end. So their masses, we have to add the masses up. Now we just plug in what we know. What do I know? I know that that is 2. And this is the square root of 2 times 9.8 times 5 sine 30 degrees, right? And what is that? 2 plus 3 times V3. So okay, should we make it more interesting? The answer is yes, we should. All right, we'll start with a similar situation. Block A. We'll just call this D and theta. And block B now, instead of just sitting there by itself, it's attached to a spring. The spring is at its equilibrium position. The box is just sitting there. We would be given the masses, the distance, the angle, the initial velocities are all 0. Let's just leave it frictionless for now. And what else do we need? Oh, we need a spring constant. And how much we're given, how much the spring compresses. So this is the initial state. And in the final state, we have A doing that, and B has come to rest. After compressing the spring by an amount delta X. So that's the information that's given. So can we go from the beginning to the end using momentum? No. At the beginning, there is no momentum. At the end, there is some. Why can't we go from the beginning to the end with momentum? Because the Earth acts on our system, right? We have an external force reaching in during that time interval, changing the momentum of our system. Can we go from the beginning to the end using energy? The answer is we don't know. So if you don't know, you can't. You can only use it if you know for sure. What do we know? We know these two blocks bounced off of each other. Maybe it's elastic. Maybe it's inelastic. We don't know. We have to be told. Are we told it's elastic? No, I don't see that in the given information anywhere. So don't assume. So in this case, because we don't know, we can't assume it's elastic. We have to assume it's inelastic, right? And go from there. What do? We break it up into smaller problems. So let's make a timeline for what's going on here. What are two times that are always on the timeline? Just before the collision and just after the collision. So just before the collision, what does it look like? B is just sitting there, and A is moving with some velocity. Just after the collision, what does it look like? A and B are both moving. Now B is attached to a spring, but we really don't care. we really don't care because the spring hasn't had a chance to compress yet. This is just a split second after the collision. The spring really hasn't had any effect yet. So what am I missing? I need to figure out how fast A is going before the collision. So I have to look at what happened before. I need an earlier time here where A is up on the hill. And then I need something later when that spring is compressed and B comes to rest. So here I have 4 times. I'm going to call this 1, 2, 3, and 4. 4 times on my timeline. What's always there? The split second before the collision, the split second after the collision, because I'm going to use momentum to get through that collision. What happens earlier? I don't know. Maybe I use energy. Maybe I use kinematics. Maybe I use something else to figure out what I need to know. What happens afterwards? I use other techniques to figure out what I need to know. But to get through that collision, I know momentum is what I'm going to do. So going from here to here, momentum. Let's set up that equation. We know we're going to use momentum to get through the collision, right? That's kind of a no-brainer. You see a collision, momentum should pop into your mind immediately. So let's write out the equation we need to get through that collision, and then that helps us think of what to do next. So I know I'm going from the split second before the collision to the split second after the collision using momentum. Let's write out that equation. I'm going to pick the right as my positive direction. This is the velocity of A at time 2, and this is the velocity of B at time 2, which I know is 0. This is the velocity of A at time 3, and the velocity of B at time 3. And this is the velocity of B at time 4. Okay? So I've got the momentum of A at time 2 plus the momentum of B at time 2, that should be a 2, equals the momentum of A at time 3 plus the momentum of B at time 3. So far, so good. We've got our equation. And what are we trying to find? We're trying to find the velocity of A at time 3, right? The velocity of A after the collision. This is what we're trying to find. This is our goal, right? Find that. If we knew everything else, we could solve for that. So let's go back and look around. The velocity that we're missing this one. And we're missing this one. So we go back to the problem. We say, what other information is there? Wait a minute. They tell us A starts out up on a hill. So I can use energy to go from 1 to 2. And that will help me find this one here. And then I know something happens afterwards. block B compresses that spring. So I can use energy to work backwards, going from 4 to 3. And what'll that do? That'll get me that value right there. Then I can solve this momentum equation and get my unknown that I need. Sometimes with these problems, there's a lot going on. Pick, something. There's a collision in the middle. You have to get through that collision with momentum. So write the momentum equation for the split second before to the split second after, and then start looking. Say, oh, this is what I'm trying to find. If I only knew these other things, I could do it. Well, then start thinking, well, okay, maybe there's some information that helps me find those other things. Okay, let's do energy going from 1 to 2. The energy at 1 is going to equal the energy at 2 because we have frictionless surfaces. If we didn't have frictionless surfaces, then we would have to account for that, right, in our energy equation. The mechanical energy at 1 equals the mechanical energy at 2. Initially, it's all gravitational potential, right? We just did that problem. And at the end, it's all kinetic energy. And so we get and of course, that's H is D sine theta, right? So there's one of our unknowns. And then we can do the other one. We're going to use energy to figure out the velocity of block B before that spring started to compress and change it. So at time 3, block B was moving with a lot of kinetic energy, 1/2 m v squared. And then it compressed that spring until it stopped moving, and all of its energy now is stored in potential energy of the spring, 1/2 k x squared. So the velocity of B at time 3, square root of k over m times now we can plug that in and solve for VA3. If we get a positive number, it's moving to the right. If we get a negative number, it's moving to the left. Yeah, when I draw my timeline here, if something hasn't changed, then I don't really care about it, right, in my timeline. So I had B sitting over here at time 1. I have B sitting over here at time 2. Do I really care? It's the same thing in both, right? It's not really changing anything. I'm using this to figure out information for A. A has not interacted with B yet, right? All I care about is A going from 1 to 2. And going from 3 to 4, A does not interact with B at all either. All I care about is B and that spring. What's happening between B and the spring? A is moving with some energy, and it continues to move with that energy forever. So it's the same in 3 and 4, but all I care about is block B and the spring. Okay. I'm also going to, I told you these types of problems are really, your physics instructors love them because we know, when you know how to solve a problem like this, that you know when you can use one, when you can use energy, when you can use momentum, when you can't. And it tells us a lot about your knowledge of energy and momentum. Our textbook has almost no problems like this in it. It's an absolute crime. I don't know how they could have put this textbook out with no end of chapter problems that deal with this. So what I will do is send out some extra problems. I'll copy from another textbook and I'll send them out. I'll email the class a PDF, or maybe I'll just post it on the website. I don't know. I'll email it probably. A PDF with some extra end of chapter problems that should be in our textbook, but they're not. So you'll be able to practice those. And we do quite a few. We're going to end up doing a fair number of them in class before we're said and done here. Okay. Let's do some center of mass. Get a jump on center of mass. We'll start with a simple system, just some point masses. Momentum in 2 dimensions is just, we did a problem last time. You just break it up into components and do 2 one-dimensional momentum problems, right? Yeah, we might do some more. We might not. but momentum in 2 dimensions is fair game. Okay, so Matt, let's throw some point masses on here. We've got, we'll stick one here at the origin. We'll call that M1. And then at 2 here, let's have M2 and M3 and M4 and M5. 5 point masses. One kilogram, 2 kilograms. Let's let 3 also be 2 kilograms. 4 kilograms. 5 kilograms. Okay, so 2 and 3 will be the same mass. Everything else will be slightly different. Our formula for point masses, it's like doing a weighted average. We're taking the sum of all the masses multiplied by their positions and dividing by the total mass. So for this case, for our 5 point objects, it's going to be M1 times its x position plus M2 times its x position, 3, 4 times its position, 5 times its position, you get the idea, over the total mass. I have 1 kilogram times what's the position of block of M1? X equals 0. So I put 0 in there. And block 2 is 2 kilograms, and it's at X equals 2 meters. Oops. And block 3 is 2 at 2 meters. And block 4 is 4 at 3 meters. And block 5 is 5 at 5 meters, right? And I add up the masses, 1 plus 2 plus 2 plus 4 plus 5, that's kilograms. And so what do I end up with here? I end up with meters. 0, 4, 4, 12, and 25 over total mass of 14. Units are meters. 3.21 meters. So my center of mass of this system, sort of the weighted average of where all the mass is located, is somewhere on the line here, x equals 3.2, 3.5, 3.2. Somewhere on that line is the x center of mass, the x coordinate of my center of mass. Now I do the same thing for the y. What am I going to get when I do my y? But where's my y center of mass going to be? Just looking at this thing, can you tell? It's going to be at y equals 0. 3 of them are right on the y-axis, and the other 2 are symmetric about the y-axis. But let's do it anyway. Each mass multiplied by its y-coordinate over the sum of all the masses. So I've got 1 kilogram times 0. The first M1 is at y equals 0. M2 is at y equals plus 2. So I've got 2 kilograms times plus 2 meters. And 3 is also 2 kilograms, but it's at y equals minus 2. And then I've got a 4 times 0, and I've got a 5 times 0. And I divide by 14. And so because of this, I get 0. That means somewhere on this line is the y center of mass. It's where they intersect, right? Right there is the center of mass of my system of 5 particles. If they were connected by massless rods, that is where we would balance it. That's the balance point. Now this is for point objects. This is our equation for point objects. We don't always have point objects. Sometimes we have solid objects, right? How do we find the center of mass of a solid object? We turn that into an integral. It's the mass. We treat each little tiny element of the mass like a point mass. We take its mass, some little infinitesimal part of it, call that dm. We multiply it by its position, and we add them all up. And then we add up all the masses to get the total mass. Okay, what is this dm? It's the mass of some little tiny part of our solid object. Let's say I had a rod. What would I do? I would find some little tiny chunk. And say that little tiny chunk of mass, I'm going to call that dm. Well, I want to know what is the mass there? What would I do? How would you find the mass if I gave you a long rope and I said, tell me how much this little chunk in the middle weighs, but you can't cut my rope? What would you do to find the weight of that little chunk in the middle? I hand you a long rope. I say, how much does whatever 1 foot length in the middle, how much does that weigh? What are you going to do? You're going to weigh the whole thing. Yes. And you're going to measure the length of the whole thing. And you'll find the density of the rope. And you'll multiply by that little length in the center to figure out how much that weighs. That's what we're going to do here. We can't dm. What is dm? We can't integrate dm, right? We've got to turn that into something we can integrate, like a dx or something else. So we'll use the fact that this dm is going to be some little tiny length, dx, and we'll multiply it by the total mass over the total length. We'll multiply it by the mass density. Now, it doesn't have to be mass over length because that only works, the total mass divided by the total length only works if the density is uniform. Uniform density, that means it's the same everywhere. If I cut a 1 foot section off of one end, it weighs the exact same as a 1 foot section off the other end or a 1 foot section out of the middle. They all weigh the same, right? That's what uniform density means. But that's not always the case. Sometimes, like if you picture a baseball bat gets fatter. So if you cut a little segment off the end, it's going to weigh a lot more than if you cut that same segment off the handle of the bat where it gets thinner, right? The density, I know it's not really the density changing because it's the volume is changing, but pretend it was a thin one-dimensional object. You could make something where the density changes and a section at one end weighs more than the same length section at the other end. Okay, so what we'll do next time is we'll continue with center of mass. You've at least seen it for point objects. And a lot of times you can treat things like point objects, even though they have, volume and size to them in a problem, but not always. And we'll continue with center of mass next time. I'm going to stop the recording. Stick around if you want to do our office hour review session that's coming up right now. And then we will have a 3-day weekend. I know that doesn't affect our class, but a 3-day weekend. And I'll see you all again on Tuesday if you're not going to stick around for the review session.